Hi everyone and welcome back to PrepFusion. So today we'll start a new topic that is on monotonicity and maxima minima. So this is a very important topic. So question have come up from this topic, right? This also comes under the application of derivatives. Okay, something has happened. Application of derivatives. Okay, this one work, right? This one work. So this is a lecture 7a. Previously we have also been studying application derivative, but that was a bit different. Will be a bit different. Okay, so before obviously diving deep into this quotient, right, into the quotients of monotonicity, we have to understand what does monotonicity means. So a function's monotonicity refers to whether the function is increasing or decreasing. It tells us the nature of the function. Okay, the nature, that is whether the function is decreasing over a range or it is increasing over a range. When a function is increasing on its entire domain or decreasing on its entire domain, we say that the function is monotonic. Monotonic means single-sided, right? It doesn't change. It doesn't want to change. Monotonic means he is very monotonous person. He is very monotonous person. That means he just goes with the flow. He doesn't want to change, right? Nobody wants any change. Okay, do you want every day we're sleeping at 10, so we want to sleep at 10 every day? Okay, we don't want change. So that is what monotonic means basically. So if the function is increasing over its entire domain, whatever value of x I give, it will always increases. That means it is monotonic. Or if it is decreasing over its entire domain, that also means it is monotonic. Okay, we can determine if a function is monotonic by observing its graph, or we can check its derivative. So there are two methods. First one is by observing graph, and second one is by checking its derivative. Okay, two methods. We'll see. Obviously mathematically, if you have to do something, obviously you have to do it derivative only, but graphically also we will see, understand it better visually. So here I have increasing and decreasing functions. So let's understand what does an increasing function mean and what does a decreasing function mean. Okay, by mistake I have marked these points. Okay, so here what do I observe? I observe that if I take this point and if I take this point, this delta y, right, has increased. It is positive. Again, if I take this point and take this point, again delta y is positive. It is always increasing. Here quite the opposite. If I take some point here, it is decreasing. The y value has reduced. Again, if I take some point here, again the y value has reduced. So it is again decreasing, right? It is again decreasing. So it is always decreasing and it is always increasing. Always decreasing and always increasing. Okay, so can we quantify this? We will quantify this, but let's first take 2 points and write this mathematically, right? So here I have x1 x2 and here I have x1 x2. What are the few things I notice? I notice that my f of x2, as my x2 is greater than x1, okay, as my x increases, my y value also increases. And what about this case? As my x2 is greater than x1, as my f of x2 increases, my y value reduces further. Reduces. Okay, so f of x2 will be less than f of x1. So y value reduces and x value increases. So this means it is a decreasing function. X value increases and y value also increases. That means it is a increasing function. Okay, so any other way you can quantify? You can quantify like this graph is what? If I say you this graph is basically e raised to power x. Okay, and this graph is basically e raised to power minus x. And what is the funny thing about this? The funny thing is this in itself is always positive, and if I find the derivative, that will also be raised to power x, and that also will be always positive. Okay, so the slope will always be positive. and here the slope will always be negative. This is an observation. You see, it is always downward, right? Downward. It is always downward. Slope is always downward, and almost it is going to zero. Here also, slope is always positive. Slope is always positive. It is increasing. Okay, so now let's understand few terminologies. So what is a strictly increasing function? Strictly increasing function. So a strictly increasing function means that my f dash of x will always be positive. Okay, f dash of x will always be positive, and it may become equal to 0 at discrete points, not continuous points. So at different point, right, different points. What do I mean by this? When we'll see the converse of this, there we will understand this better. At different points. Okay, discrete mean different points. Here slope, I will write f dash of x. I will write few things, just hold on a second. So this is what I wanted to write, that it will be always greater than 0, and but it can become 0 at discrete points. In this case, if you see y equals to x cube, the slope is always positive. Okay, always positive except at x equals to 0. At x equals to 0, the slope is also 0. Okay, here f dash of x at x equals to 0 is 0. It is 2x 3x square, which is 0. So this is the point you have to note. Let's come to another functions, and there we'll understand this better. So this is strictly increasing function, and this is non-decreasing function. Both are almost similar, except the difference is it can be 0 at continuous points. Okay, f dash of x can be 0 at continuous points. F dash of x can be 0 at continuous points. What do you mean by this? Previously also you said f dash of x can be 0, but at discrete points, at single value points or different points. Here I am observing from alpha to beta, it is always 0. F dash of x is always 0 in this range. Then can we call this strictly increasing function? No, we can't call this strictly increasing function. Why? Because here from this alpha to beta, this is not increasing, this is remaining constant. Okay, this is remaining constant, but after beta this is always increasing, and before alpha this also is always increasing. But between these, this is a large range. Hence I can't say this is always increasing, but I can say this is always non-decreasing. Because is this ever decreasing? No. Here also this value is going up, then it stopped around here and it remained constant. But did it decrease? No, it did not decrease. So I can name this as non-decreasing. Again, after this beta, it kept on increasing. So it satisfies a non-decreasing. So that is the difference between a non-decreasing and a strictly increasing function. Strictly increasing function means it always increases except at finite discrete points, right? At discrete points, the f dash of x can be equal to 0. After that, again, it will start increasing, just like here. But non-decreasing function means it won't always increase. Okay, but it will never decrease. That's why this is known as a non-decreasing function. Okay, here I have also classified this the different things is here. what is a strictly increasing function? Strictly increasing function can also be said as monotonically increasing function. Monotonically increasing function, and a strictly decreasing function can also be said as monotonically decreasing function. Okay, these two things are same only, and this is the classification. Again, this e raised to power x and this e raised to power minus x. Okay, this is a perfect example. Perfect example. So here my derivative will always be equal to 0, or it can be always greater than 0, or it can be equal to 0 for discrete points. Here for strictly decreasing function, my derivative should always be less than 0 or be equal to 0 for discrete points. Okay, these two are the things. Now what do you mean by non-decreasing function? Non-decreasing function can also be said as increasing. Sorry, non-decreasing function can also be said as increasing. Non-increasing function can also be said as decreasing, because these are strictly increasing or strictly decreasing. I am just saying increasing with low pressure. Here when I'm saying strictly increasing, right? Always should increase. But here I'm saying okay, increasing. Okay, so this increases, but it may happen sometimes it remains constant, then again it starts increasing. Okay, it doesn't always increase. Always increase, it can remain constant. That's why we can name this as non-decreasing function. And here what do we say? We say okay, this is decreasing, but sometimes it may stop decreasing. This may remain constant. So if it is constant, that means it is a non-increasing function, because it will never ever increase over its domain, but it can stop decreasing. That's why we can either say these two things. I hope you can understand this. So here, right, f dash of x has to be greater than equal to 0 for all real x. Again, f dash of x has to be less than equal to 0 for all real x for non-increasing, and this is for non-decreasing. Okay, so obviously this strictly increasing function falls into this category of non-decreasing function, because as it is always increasing, I can say this is non-decreasing function. Yes, this as is always decreasing, I can say this is a non-increasing function. Does it ever increase? No. So obviously these are falling in this category. But you have to understand the differences between all of these four classifications. Oh, okay. So I have written in key point: if f of x is strictly increasing, then inverse of f of x is also strictly increasing. Similarly, if f of x is strictly decreasing, then inverse of f of x is also strictly decreasing. Okay, so this is the case. Why is this the case? So, like, you can do, like, this is homework for you to derive. Okay, derive this at homework. So f dash of x, okay, derive. You just try to understand, like, take any function which is always increasing. Let's say you take e raised to power x, then you find the inverse of that, then you try to understand why is it always increasing. So yeah, what you can do, you write y equals to e raised to power x. Now you write x equals to e raised to power y. Okay, from there you will be able to understand this thing. Okay, then the second point: if f of x and g of x have the same monotonicity, both increasing or decreasing on a b, then f of g of x and g of f of x are monotonically increasing. Again, this point is very interesting. So they have same monotonicity, either they are increasing or decreasing. So let's take for the first case that both increasing. Okay, I will take this to the next page. For the second one, that both are increasing. So if both are increasing, what does that mean? That means that as I increase my x, my f of x will also increase, and my g of x will also increase. Okay, as I increase my x, f of x will also increase, g of x will also increase. Okay, next I am more interested in the composite functions, f of g of x and g of f of x. So what is f of g of x? So f of g of x means, now let's see what happens if I increase my x. So if I increase my x, what does that mean? That means that my g of x will increase. Now if my g of x is increasing, that means my f of g of x, this value is increasing, right? This value is increasing. Now I know if the inside bracket increases, then this f of x also increases, as the same case over here. So my f of g of x will also increase. Okay, So we came from here to here, so monotonicity is unchanged, it's still same. So you can derive for the others. I've just given you example, you can derive for the others. Okay, next is this: if g of x and f of x have opposite monotonicity, then f of g of x and g of f of x are strictly decreasing. Okay, are strictly decreasing, and this is always monotonically increasing. Okay, so if they are same, they will be always increasing. If they are different, they will always be decreasing. Okay, you can prove it again using this method. I won't go into this method, you can prove it using this method. We don't have time, that's why I'm skipping this. Okay, you can prove it for yourself like that, just how I proved it. Okay, now what is monotonicity in an interval? So we have to find the intervals where the function is increasing or decreasing. So now the question comes up, right? Question comes up. We have to find the interval where the function is increasing and decreasing. So where will the function increase? The function will increase where my slope is positive. I just found out here, right? I just found out here. I did the classifications and I told you they're talking about increasing. So I will only talk about here. The slope can be greater than equal to 0, and it will be decreasing where the slope is less than equals to 0, in that range. So that is exactly what I'll do. Okay, so so for that I have to obviously compute the f dash of x. So obviously whenever monotonicity question comes up, you have to compute the derivative. So what is my f dash of x? Simply it is I will apply the quotient rule. So it will be ln x minus x by x into ln x whole square minus 1 ln x whole square. Okay, so this is my derivative basically. Now for the function to be increasing, my f dash of x has to be greater than 0. So like I'm talking about strictly increasing only, it has to be greater than 0. Okay, so now obviously for this, my ln x minus 1 divided by ln x whole square has to be greater than 0. So if it has to be greater than 0, so x, like I can write ln x has to be greater than 1. When is my ln x greater than 1? So ln of e is 1, and if my x is greater than e, obviously it will be greater than 1. So x has to be greater than e. Now what is my range in this case? The range will be x belongs to e comma positive infinity. So this is the range where my function is increasing always. Okay, now let's do the for it where my function is always decreasing. Okay, so again I will write the same things, just the inequality will change. Inequality will change. So this will be less than 0. As my ln x is not equal to 0, I can simply cross multiply on both sides. Again this will be less than 0, less than 1. So obviously my x will be what? X will be less than 1, right? X will be less than e, sorry, not 1. X will be less than e. That means the pattern will be a bit different this time. The pattern will be minus infinity to e. Okay, but are you missing anything? Are you missing anything? I mentioned here also that whenever I'm doing this cross multiplication, right? So I'm assuming that my ln x is not equals to 0. So obviously my x cannot be equals to 1, then ln of 1 is 0. Okay, here also, because this was not lying in this range, obviously I could have simply ignored it, no worries. But here, right, as my x is less than e and greater than minus infinity, 1 is lying, x equal to 1 is lying in this range, and I can't include x equals to 1 because at x equals to 1 function not defined. Okay, the derivative not defined. So obviously again the same thing, ln x equals to not equals to not 0, not equals to 1. So x is not equals to 1. So obviously I have to rewrite this thing. This will be something like this will be 1 union 1 comma e. Okay, so it will be something like this. Okay, so yeah, this is how you solve a monotonicity question. Now let's solve this. The function f of x is defined like this. You have to find out whether it is decreasing, increasing or decreasing. So basically you have to comment about the monotonicity. Okay, about the range. So what you can do, you can obviously first go for the derivative. What is the derivative? Derivative is this f dash of x will be e raised to power minus x plus minus of e raised to power minus x into x plus 2. So let me just think about something. It is telling me decreasing for all x. Is it really so? Decreasing for all x. So I can equate this with less than 0 minus x minus, so this will be x will go that x plus 2 is greater than 1, x is greater than minus 1. No, this is not the case, right? Only when my x is greater than 1, this is always decreasing, okay, and not the case. So this first option is gone. What about my second option? Decreasing in minus infinity to minus 1 and increasing in minus 1 to plus infinity. So for that I have to check f dash of x greater than 0. So again, only the inequality will change this time. E raised to power, I will write so x has to be, okay, am I doing this correctly? Yeah, greater than 0. So this x has to be less than minus 1. The x has to be less than minus 1. So basically, is there any point of discontinuity? No, there isn't, right? There isn't any point of discontinuity here. Is there any point of discontinuity here? No, right? There isn't. Okay, something vibrated, sorry for that. So basically here the range is x belong to minus 1 to positive infinity, and here the range is x belongs to negative infinity and minus 1. Okay, at x equal to minus 1 we have a like a discrete point where this thing is going to 0, e raised to power minus 1 minus this also e raised to power minus 1, this is going to 0. So at x equals to 1 discrete point it is 0, okay, neither increasing neither decreasing, okay, but here in this range it is increasing, in this range it is decreasing. Okay, so obviously it is not increasing for all x, it is decreasing in this range, yes, correct, and it is increasing in this range, yes, correct. Okay, so increasing in this range and decreasing in this range, yeah, this option D is correct. So let's go to the next question. So here the function is defined f of x equals to x into e raised to power this. Now again, right, you're talking about monotonicity. What you can do, again you can find the derivative. Okay, again you can find the derivative. So my f dash of x will be simply equals to chain rule I will apply, e raised to power x into 1 minus x plus x into, if I differentiate, this is x minus x square, which is 1 minus 2x, and this is e raised to power x 1 minus x. So obviously what is it talking about? Increasing, decreasing again. So again I will talk about when this is greater than 0, when this is less than 0. So obviously, can this ever be equal to 0? No, this cannot be equal to 0. Okay, this can never be equal to 0. That is one thing. Or can it be? For it to be equal to 0, it has to be negative infinity, which is obviously not possible, but this can be equal to 0, right? That is one interesting fact. So now my f dash of x greater than 0, increasing. So what I can say, e raised to power x into 1 minus x 1 minus 2x, I had a x also here, this is e raised to power x. So this will be simply 1 plus x into 1 minus 2x. Okay, sorry, this is not equal to 0. This has to be greater than 0. Greater than 0. This becomes minus 2x square plus x plus 1 has to be greater than 0. Now the interesting fact is, if I find out the roots of this and if I use the wavy curve method, okay, if I find out the roots of this and if I use the wavy curve method, then I will be able to plot this, right? I will be able to plot this. So okay, let me do one thing. Let me not equate with this with greater than 0. I will write this as okay, I have to equate this with greater than 0. Okay, sorry, I have to equate this with greater than 0. So like I will plot this function, right, wavy curve in roughly. Okay, what are the roots of this? Can you tell me the roots of this? So what you observe is the roots of this, right? Here I'm assuming obviously that e raised to power x 1 minus x is not equal to 0. This assumption is already been taken. Okay, so if this assumption is already been taken, what do you mean by this? So basically now if I like, what are the roots? The roots are minus b upon plus minus ab, or you can say that the multiplication has to be 1, the summation has to be also 1. Sorry, 1 by 2 and 1 by 2. So yeah, let us solve anyways. I'm not able to figure this out, so I will solve. Minus 1 plus minus b square minus 4ac, and this is minus minus plus, so this will become minus 8 divided by 2a, 2 times 2 minus 2, that is, so this will become minus 1 plus minus under root 9, which is 3 divided by minus 4. So either this is become minus 4 by minus 4, which is 1, or 2 by minus 4, which is minus 1 by 2. Okay, so I have two roots, one is minus 1 by 2 and one is 1. So what is interesting over here, if I tend my x to infinity, if my x goes to infinity, what will this overall thing go to? This has highest power and it has negative sign, so it will go to minus infinity. It will be something negative. So obviously I will start from something negative. Okay, then here x equals to 1, what will happen? It will be something positive, right? Why? Because this I can write x plus 1 into x minus 1 1 by 2. Okay, so if my x is greater than 1, what is happening? Sorry, am I making some mistake? That is what I'm thinking about. This is positive, this is negative coefficient. Negative around 1, yeah, this is fine. So if my x is greater than 0, this will be positive, it is saying. Okay, I'm factorizing it wrong actually, because this is negative coefficient, right? So what I can write like this, put a negative sign over here, because this x square, right, x square has a negative coefficient, so I'll put a sign of negative sign over here. So now if my x is increasing, this thing is positive infinity, but I have a negative multiplied with it, so this will be negative infinity. Now at around x equals to greater than, like, let's just less than 1, this thing is what? This thing is negative and this thing is positive, right? Less than 1, this thing is positive anyway, this is getting added anyways. So this is positive, this is negative, overall negative times negative is positive again, so this will be positive. Then again at x equals to half, you can see the wavy curve method. This thing also goes to negative, this thing is already negative, positive, and I have a negative sign at the front, this will be negative again. Okay, so this is the case. So here, what is this? What is this thing? This is just simply equating with 0. This is simply the f dash of x, because this, right, this thing is anyways always increasing as x is increasing. Okay, just hold on a second. As x is increasing, okay, I can ignore this because I'm just equating this with greater than 0 or less than 0. I equate this with greater than 0 or less than 0. Okay, so yeah, this can this ever go to 0? No, this cannot ever go to 0. Okay, so Okay, so what I can say is that in this range my x is always increasing. Okay, in this range x is always increasing, and in this range x is decreasing. Sorry, not x, f of x. Because the slope is negative always. This is what? This is a slope only, right? This is slope only. The thing is that this quantity, if I take this common, this is anyways positive always. Something exponential is positive quantity, it can never go to any negative. So I don't care, this won't change my signs. Okay, only this part will affect my sign, so I'm only interested in this. So around minus half to 1, x belonging to minus half to 1, this function is always increasing. So minus half to 1 always increasing, so B will be my answer. Then increasing for all x, decreasing for all x, no, incorrect. Decreasing in minus half to 1, no, this is again wrong. Okay, only like this is anyways MCQ question, so only this option B will be my correct answer. Okay, so yeah, let's now go to another pattern of question, another type of question. So here they have given us that the value of a in order that f of x equals to sin x minus cos x minus ax plus b decreases for all real value. So it has to be decreasing for all real values of x. Okay, it has to be monotonically decreasing function. So what is the condition? F dash of x has to be always less than 0. That is the condition, right? For it to be decreasing always. So what we'll do, we'll find the derivative. F dash of x, that will be my cos x minus, and this will be plus sin x minus a 0. It has to be always less than 0. So a has to be greater than sin x plus cos x always, for all x, for all x, for all x. Now do you know the maximum value of sin x plus cos x? The maximum which the cos x and sin x can get, the maximum value is basically root 2. If you know this, well and good. If you don't know, then you have to find it out. Okay, so how you find it out? So you take another function g of x, which is equals to sin x upon cos x, and you find its maxima. Okay, you like, I hope few people know about maxima. If you don't know, don't worry, we'll study this later on. But you find its maxima. G dash of x equals to again cos x minus sin x equals to 0, and I find out that x equals to pi by 4 when sin x equals to cos x. We either get maxima or minima. Okay, or it can be minus pi by 4 also. So this g of x can vary between what? G of x can vary between minus root 2 and plus root 2. Okay, minus pi by 2 plus minus root 2 and plus okay, minus not minus pi by 2, some other value, 3 minus 3 pi by 2 or something like that. Okay, so yeah, this you have to remember. So the maximum value that this function can take is root 2. If my a is greater than that maximum value, okay, then it will always be a decreasing function. Okay, so a has to be greater than this maximum value, which is root 2. Okay, so this is how you solve this question. A has to be greater than this root 2. Okay, it goes between minus root 2, and I will take the maximum value over here, and the maximum value is root 2 for this case. So a has to be greater than the maximum value of this sin x plus cos x. So root 2, a greater than root 2 will be my answer. Let's come to the type 3 of questions. This one was the pattern 2, where they have told you that it is monotonically increasing. Now you have to find some parameter. Beforehand they were asking you what is the monotonicity of the function. Now they have told you the monotonicity and you have to find out some other parameter. Okay, and type 3, what is type 3? Type 3 is this types of inequality, right? You have to prove, but like obviously you might ask, sir, how can proof come in examination? Proof won't come, but this method what we will use, right, it will be helpful in the some other question. It will help you in some other question, some other type of question they will ask you. Okay, so here they are asking us to prove that sin x will always be less than x and tan x will always be greater than x for x belonging to 0 to pi by 2. Okay, so what we can do, so it is talking about sin x is less than x, so I can take this portion. Okay, so I can take this portion, case 1, there is a debate that sin x is less than x. Now this is the debate, right? This is a debate. So sin x is less than x. So if sin x is less than x, that means I can rewrite this sin x minus x has to be less than 0. Okay, now I can take this function, right? I can take this function and find the derivative and check whether the derivative is always less than 0 or not 0. Okay, so this I can write as f of x. Okay, so now my f of x equals to cos x minus 1. Okay, equals to cos x minus 1. So here let me check whether this is always greater than 0 or less than cos x can at max like vary between minus 1 to plus 1. Okay, it varies between minus 1 to plus 1. So at max it can go to 0. It can go to 0. Okay, anyways it will always lie in the bottom side, right? Always negative, always negative, always negative. Everything is recording, right? I have to check, else I will die. Yeah, always negative. So if my f dash of x is always negative, what does that mean? I'm doing the back calculation right now. So if my derivative is always negative, that means it is always decreasing. Okay, always decreasing. So what does this mean? If f of x is always decreasing, what does this mean? So let me calculate the endpoints. So f of 0 is what? Sine 0 minus 0, so it is 0. Okay, and as my x increases, as I know that this will decrease, so f of x will be reducing, hence f of x will be reducing from 0. That means f of x is something negative. Okay, yeah, negative between x belonging to 0 to pi by 2. Because if you put cos 0 over here, what is this? 1 minus 1, 0. If you put cos pi by 2, this will be 0 minus 1, which is minus 1. So this will vary from 0 to minus 1. Okay, because cos x is something like this. Cos x is something like this. Okay, so yeah, this is the case. So right now f of x is negative. So as it is negative, that means this is always less than 0. That means in the domain, that is sin x minus x less than 0. Hence I can say sin x is, you write this properly, hence I can say sin x is less than x. So this is proof, right? Between x belonging to 0 to pi by 2. Okay, this is the first case that I proved for. Let's go for the second one. If I go for the second one, this will be x is less than tan x. Okay, that means x minus tan x has to be less than 0. Again I will take this as f of x or g of x this time. So my g of x equals to x minus tan x. Now if I differentiate, what will happen? Just hold on a second, let me check if this is recording or not. Yeah. So if I differentiate g dash of x, this will be x minus, not x, sorry, 1 minus sec square of x. What is sec square of x? Sec square of x is this, right? It is 1 by cos square of x. Okay, so it is simply cos square x minus 1. I can write this as something like this, and cos square x, this will be minus sin square x. Equals to minus tan square x. Or if you don't want to write it like this, okay, just simply write it like this, x square x. So between these range, right, between 0 to pi by 2, sec of 0 is what? Sec of 0 is 1 itself. So it is again vary from 0, and sec of pi by 2 is what? It is infinity, right? It is infinity. Sec of 0 because cos pi by 2 is 0 and 1 by 0 is infinity. So this is going to infinity. Okay. Why is the case? I am mentioning as my x is 0, this will be 1. So 1 minus 1 is 0. After that, sec of x will only increase because cos x will only decrease because cos x decreases. Now this is 1 by something decreasing, so hence this overall thing will increase. I hope you got the point. If you don't, just replay the video. Okay, so this is only increasing after this. So if it is increasing to infinity. So 1 minus infinity is minus infinity. So it is going from 0 to minus infinity. So hence I can say my g dash of x is always less than 0 for x belonging to 0 to pi by 2. Okay, now what I can say, is that what will happen to my this side, what will happen to my g dash of x, what will happen to my this function. So this function is g of x is decreasing in 0 to pi by 2. Okay, g of x is decreasing in 0 to pi by 2, and yeah, that is the case. So next what? So as it is decreasing always, hence I can say what is g of 0? Again, g of 0 is 0, and if it is decreasing after this, so g of x will be negative for x belonging to 0 comma pi by 2. Hence as g of x is negative, then this will be always less than 0, that is x minus tan x will always be less than 0. Hence again inequality proved, x is less than tan x. Okay, you could have solved this the other way around. How? Basically what you could have done is you could have shifted this x to this, then you could have written g of x as tan x minus x greater than 0, and from there also you will get similar result. Okay, so hence proved. Okay, hence proof. Now let's solve another question. The set of values of x for which ln 1 plus x is less than x. The set of values of x for which ln 1 plus x is less than x. So again you will try to use that same pattern, right? Same pattern. What you can do is ln 1 plus x is less than x. Hence ln 1 plus x minus x has to be less than 0. Next, you think this as f of x. So this is my f of x, 1 plus x minus x. Then you find the f dash of x. this is 1 by 1 plus x minus 1. So this will be 1 minus 1. So this is minus x by 1 plus x. Okay, so what you have to find out? You have to find the set of values of x for which ln of 1 plus x is less than x. That is, this is negative. What is now I am seeing the range 0 and 1. Seeing the range 0 and 1. So what is x equals to 0? X equals to 0, if I put this 0 is less than 0. So if I put x equal to 0, that means this is 0. Okay, f dash of 0 is 0. F dash of 0 is 0. Now if I want to put something higher than x equals to 0, this denominator will be positive, this will be positive, positive by positive will be positive, but I have a negative sign, so I will get negative. So for x greater than 0, my f dash of x will be less than 0. Always f dash of x will be less than 0 always. Okay, positive upon positive is positive, and I have a negative sign at the front, so it will be negative overall. If this is always negative, always decreasing, so I can say my f of x is always decreasing. Now if my f of x is always decreasing, and what is my f of 0? I am starting from 0 itself. F of 0 is, again, f of 0 is what? ln 1 minus 0 is 0 itself. 0 minus 0 is 0. So here again this point comes in factor, it is always decreasing, so it will only go down from 0. It can only go down from 0. So this f of x has to be less than 0 for x greater than 0. Okay, for x greater than 0, it will only go down from here. Okay, so yeah, let's put f of x. What is f of x? F of x is ln x hence proved, right? That is ln 1 plus x less than x. Okay, for x greater than 0. So if x is greater than 0, it is basically all this inequality is always satisfied. Okay, so yeah, this is how you solve this question. Like you can solve this graphically also, but you don't need to solve graphically. So next is, we'll start with maxima, minima, and what we know about maxima and minima. So basically, what does maxima and minima means? Maxima, minima are basically points of extremum, points of extremum. Okay, so what do you mean by anything extreme? Extreme means either it's very high or very low, nothing in between. That's why they are known as maxima and minima, points of maxima and minima. So up until now, what you should do, like in your undergrad or high school, what you have done, you find the derivative, that is dy upon dx f dash of x. You have made this equals to 0. Okay, you have made this equals to 0 for maxima or minima. Either you will get maxima or minima. Maxima or minima. Okay, either you will get maxima or minima. Then what you do, you take the second derivative of this, d square y upon dx square, which is f dash of x. Now you put those whatever values of x you found over here, you put those value over here, and there can be 3 cases up right now. So after putting the values of x, f double dash of x, there can be 3 cases. What are those 3 cases? One is if it is positive. If it is positive, that means I will get a minima. If it is negative, that means I will get a maxima. Of course. Now, the third case, if it is 0, if it is equals to 0, what do I get? If it is equals to 0, I don't know. You will say that I will get an inflection point, right? Point of inflection. I will say you are not. Because not every time when my double derivative is equals to 0, I will get a point of inflection. This is not completely true. This may be true, but this is not completely true. So I will write here, not completely true. Why is this a case? We'll understand this, okay, with examples and all those things. We'll understand this, okay. So also one more thing, that let my f of x equals to mod of x. Let my f of x equals to mod of x. In that case, how will the graph look? The graph is this. Graph is something like this. Now, is the function differentiable? The function is non-differentiable function, okay, non-differentiable function, differentiable. Okay, so if the function is non-differentiable, that means minima exist or doesn't exist. Like maximum minima can exist or not, but graphically I can say minima exist. Graphically I can see minima exist, but function is non-differentiable. How can this happen? Okay, how can this happen? So one thing is for sure, I have a minima over here, so that means it is not necessary that function has to be differentiable for minima or maxima to exist. Okay, not necessary that f of x will be differentiable. Okay, not necessary, but still minima and maxima can exist. Minima and maxima can exist. It may not be true. Also, it may so happen it doesn't have to be continuous. Then also minima and maxima can exist. I'm talking about local minima and local maxima. Okay, so we'll learn more about that just in this slide. So here we'll study about the concept of local minima and maxima. What do we mean by this? This means the relative minima and maxima, relative to its neighborhood. Local means neighborhood, right? Neighborhood, just beside me. So I will write here relative to my neighborhood. Okay, relative to my neighborhood. So what is the concept of local maxima and minima? What is the concept? So basically here, if you observe, let's talk about this point E. So just before this point and just after this point, all the point values are lower than this f of a. Okay, so I will say this as concept, I will say this as local maxima, because locally this is the maximum point. Obviously this graph can go along and anywhere, right? I can't see the complete graph, complete graph. Okay, here can't see the complete graph. Now if I can't see the complete graph, so how will I find maximum minima? So I have to make some concept, right? Make a concept that is meaningful to me. So I want just in between this range, what is my maximum minima? So if I am talking about some range, so I will talk about local maximum minima. So relative to its neighborhood, this is the maximum. Okay, it may so happen after this the graph may increase more than this value, and that will be my another maxima. But in this particular range, my maxima is this. So mathematically, how I can represent this? Mathematically, what I can write is that my f of a is greater than f of a plus h. Also, it is greater than f of a minus h. near its neighborhood, it is greater than everything. Okay, same thing for minima also. Here I can observe that this f of a is less than this f of a plus h and this a minus h. So I can write f of a is less than f of a plus h and f of a minus h. Okay, so yeah, that is the case. Now let's solve a question and we'll understand this. So find the number of points of local maxima and minima for the function. So it is asking us about the local minima and maxima. Okay, local minima and maxima. So what we should do first, we should plot the function, because this function mathematically solving is very difficult for me. So first what I'll do, I'll just remove all the mods. I will plot some g of x equals to x square minus 5x plus 6. So if I plot this, okay, so this will be something like this, that now g of x equals to x square minus 5x plus 6. So this is a parabola, and I can further break this down, that like we can factorize this x minus 2 into x minus 3. Okay, this is my g of x. Now obviously very simple, so this is like a wavy curve only. So at x equals to 2 and x equals to 3, I will have roots. So x equals to 2 and x equals to 3, I will have roots, and my graph will be like this parabola. Okay, and x tending to infinity, it will go to positive. X tending to minus infinity also would go to positive, because I have a x square over here. Okay, this is the graph. I won't explain much over here. The y intercept will be 6, because I will put x equal to 0, and the x intercept will be, if I put y equal to 0, it will be 2 and 3 obviously. So that is how we found out the roots. So now let's solve for, now if I replace x with mod of x, so we replace x with mod of x, what will happen? I hope you are remembering the graphical transformations. Obviously whatever is present on the left hand side, I will delete that, and whatever is on the right hand side, I will copy that here. It will just be a mirror image. So I will exactly do that only. So this will be minus 2 minus 3, and it will be just a mirror image. Okay, so next what? Next, because this if I replace x with mod of x square is anyways x square, because that is always positive, right? Mod of x square is anyways x square, it is always positive. That's why this is written like this. Now I will take the mod of whole function. So this is simply g of mod of x. Now if I take the mod of this whole function, whatever negative we have, this mod function will just make it positive. So I will again just copy this. Okay, so now can you tell me about the local maxima and minima? So what is the minimum point? 0 0 0 0, right? And so these are my minima points, because just before this and just after this, just before this, just after this, everything is increasing. Okay, so I will say, just hold on a second. X equals to minus 3 minus 2 2 and 3 are points of local minima. Okay, are points of local minimum. Now let's write about this, right? Let's write about x equals to 0. So here what I'm observing, just before x equal to 0, just after x equal to 0, everything is reducing, and at x equal to 0 I have a maximum point, x equal to 6. So obviously this x equal to 6 will be point of local maxima. Why are these local? Because I haven't drawn the graph fully, right? I haven't drawn the graph fully. I've just drawn a part of it. Okay, obviously it will keep on increasing, it will keep on increasing. So there isn't any global maxima and minima. We'll study about local maxima, global maxima minima later on. Okay, but in this graph there is like the global maxima, it is keep on increasing, but the global minima is this x equal to 0, because obviously the mod function can never go below 0. So I have 4 minimum points and 1 maxima points. Okay, find the number of points of local maxima and minima of the function. So obviously 4 in this case, 4 and 1 in this case. Okay, 1 in this case. So like let's study about a point that is known as stationary point. What do you mean by stationary point? So now be attentive, because we will be studying few things which are very important. Okay, so in continuous function and differentiable function, the maxima minima occurs at a point where derivative is 0. Wherever my derivative is 0, maxima and minima will occur, that is for sure. Maxima or minima will occur. Okay, that is for sure. Now these points are called stationary points. Basically wherever my derivative is 0, okay, these points are called my stationary points. So here my f dash of a will be equals to 0. Here my f dash of a will be equals to 0. It can be either maximum or minima. It is called stationary point. Simple example. Okay, now one more important fact is that stationary point may or may not be points of maximum minima. Okay, so the definition of stationary point is the derivative of the function has to be 0. But if the derivative of the function is 0, it doesn't necessarily mean that my function will have a maxima or minima at that particular point. So what is the best example? The best example is my f of x equals to x cube. This is the best example. So if I draw the graph for this, x and this f of x. So if I draw the graph for this, the graph will look something like this. Okay, not exact, but it will look something like this. Around x equal to 0, this will almost go to 0 slope. Okay, so this is f of x equals to x cube. Okay, so basically what does it mean? That if I keep increasing my x, right, if I keep increasing my x, this slope is increasing and it is decreasing here, and this is going to 0 over here. Here f dash of x equals to f dash of 0 equals to 0. But is this a point of local maxima or minima? No, right? This is not a point of local maxima or minima. So neither okay, I've forgotten the neither local maxima or minima. Okay, neither local maxima or minima. So I don't have like not local maxima, not minima. So it doesn't necessarily mean that if my f dash of x equals to 0, I will get a maximum minima. So it doesn't necessarily mean that if I have a stationary point, that stationary point will be maxima or minima. Okay, so this was about the stationary points. Now let's understand what does critical points mean. Maxima and minima occurs at critical points. These points include stationary points also. Okay, so what does this mean? Like critical points will also include stationary points. If f dash of x equals to 0, okay, then also they are known as critical points. So this definition is definitely for stationary points, right? Stationary points. Now, if f dash of x does not exist, that is point of discontinuity or non-differentiability, those points are also my critical points. Those points are also my critical points. Okay. So maxima minima can occur at I should write can occur at critical points. Maxima minima, because you will be confused, right? You will say that it should occur in all of the critical points. No, that is what the confusion lies. Here again the same thing, like maxima minima can occur at points where derivative 0. Can, but not always. Not always. Here also maxima minima can occur at critical points, but not always. These points include the stationary points. Basically, f dash of x equals to 0. Critical points include stationary points, and where my derivative doesn't exist, or I have a discontinuity, okay, or where my derivative doesn't exist. So critical point includes stationary points or tangential points. Basically, tangential means where my f dash of x is 0. Okay, tangential. Basically, stationary points mean f dash of x equals to 0. Then points of discontinuity. Critical points include points of discontinuity and points of non-differentiability. All these three it includes. Okay, so let's read few key points. Points of discontinuity can be points of local minima or maxima. It may so happen. We'll understand that. Points of non-differentiability can be points of local maxima or minima. All points where maxima and minima occurs are critical points. So wherever maxima minima occur, definitely it will be critical point, but all critical points are not maxima minima. This is exactly what is written in the fourth statement. All critical points may not be maxima or minima, but all maxima minima, wherever maxima minima occurs, those will be my critical points, 100% sure. Okay, I hope you are grasping the concept. If you don't, just repeat the video. Okay, so then question is, okay, I have forgotten to write the question number up here. That is unfortunate. This one should have been a question. That is fine, we will miss a question. Identify the local maxima, local minima, or none, right? Neither of local maxima, local minima at x equals to a. Like, identify if the points are local maxima, minima at x equals to a, b and c. Okay, or none. Okay, identify whether the points are local maxima, local minima, or none at x equals to a, b, c. Okay, you have to identify this. So basically what you do, first let's take point b, right? B is a easy one because here there is no discontinuity and it is continuous, and differentiation also exists. So around point b, okay, x equals to b, what I can observe? I can observe that f of b plus is lower than f of b. Also f of b minus is also lower than f of b. So obviously it will be a local maxima because it is higher than its neighborhood. Okay, higher than its neighborhood, hence it will be a local maxima. Let's talk about c right now. Let's talk about c. So basically if I talk about c, this is c plus. Okay, now just after c, this value is higher, right? Just after c, whatever value I have here, this value is higher just after c. Okay, because this is discontinuous. Just after c, I will directly find here, right? I will directly point to here. And just before c, again this point is higher than this f of c. So obviously my f of c plus is higher than f of c, and f of c minus is also higher than f of c. Okay, so that means that what do I have? I have a point of minima because everywhere else in the near neighborhood the points are higher than the f of c. So this means I have a local minima. Okay, Next, third point. So you can observe correctly that even though the differentiation doesn't exist, right, at this point the differentiation doesn't exist, like there is discontinuity, not differentiation, there is discontinuity, but still I can able to compute the local maxima and minima. Now let's talk about x equals to a. If I talk about x equals to a, just f of a less than a and f of a greater than a, just before this point this value is lower, just after this point this value is higher. So I can say f of a minus is lower than f of a is lower than f of a plus. Now can I conclude anything? Okay, can I conclude anything? No, right? I can't conclude like local maxima or minima. What I can conclude is this function is increasing monotonically. Function, because just before it was lower, then it became higher, then again it became higher. So function is increasing monotonically. Okay, so function is increasing monotonically. Okay, so this is what we can conclude: neither maxima nor minima, neither maxima nor minima. Okay, so yeah, this was the question. I hope you understood. If you don't, like, you can repeat again. So now let's understand how do we find maximum minima. So first one is derivative test. Very simple, applicable only for differentiable functions. So up until now we have been doing derivative test only, like in your undergrad or in your high school, how you used to find maximum minima, you used to differentiate. But when you used to differentiate, you didn't know that obviously the function has to be differentiable, then only you can differentiate. Obviously this test fails when the function is not differentiable. Okay, so I will write test fails when function is non-differentiable. So test fails when function is non-differentiable. Okay, so like this gives the points of local maxima, local minima. Further analysis is required for global maxima and global minima. Okay, so if you want to find global maxima minima, further analysis what to do. So what is basically first derivative test? Basically, if f dash of x changes from positive to negative at x equals to a, then f of x has a local maxima at x equals to a. So if f dash of x changes from positive to negative, if f dash of x changes from positive to negative, that means f of x will have a local maxima at x equals to a. Why is it the case? Because here what is happening, my slope is reducing, gone to 0, then it reduces further. Okay, then it reduces further. But the important point is it was positive, then it became negative. So if my slope, okay, let me write this, f dash of x greater than 0, then in this range f dash of x less than 0, and here f dash of x equals to 0. So my slope gone from f dash of x is moving from positive to negative. Now what does this mean? My slope is reducing, that means at some point there will be a point where my slope is equals to 0. Okay, as it is reducing from positive to negative, there will be some point where my slope is 0, and if my slope is 0, obviously you can say that it will be stationary point, and stationary point can have local maxima and minima. Okay, so f of x has local maxima and minima. And similarly again you can do this. Okay, I will just draw the slopes here. Similarly you can do this. That if my f of x is moving from negative not f of x, f dash of x is less than 0, f dash of x is greater than 0. So my f dash of x, basically I can say f dash of x is moving from negative to positive, right? F dash of x is moving from negative to positive. So if my f dash of x is moving from negative to positive, so basically I will have a point of minima, because at some point it will be 0, and this means my f dash of x is moving from negative to positive. This means like the derivative is increasing. So if the derivative is increasing, then the function will also increase after this point, right? Function will also increase. If the derivative is positive, that means not positive, okay, if the derivative is increasing, what does this means? If the derivative is increasing, and it is increasing from negative to positive, so just before it is negative, okay, as it was negative, that means my function is reducing. As my derivative is negative, that means my function is reducing. Then suddenly it becomes 0, okay, and then again my derivative became positive. If my derivative became positive, that means my function is increasing. Simple concept of monotonicity, okay. If my derivative is negative in this range, that means my function is reducing. If my derivative is positive in this range, that means my function is increasing. At some point it was 0, that means my function was doing nothing, okay. Here the function was doing nothing, basically it was stationary. That means I have a point of local minima, because previously it was decreasing, then it was increasing, hence point of local minima. Similarly here, previously my derivative was positive, hence function was increasing. Then after this, function was decreasing because my derivative become negative. So at this point the derivative was 0. If the derivative was 0, that means it remains stationary. That means it reached a point of local maxima, because before it was increasing, after it is reducing. That means I have a local maxima. Simple definition of the starting slide, okay. So yeah, here one important point: f dash of x does not change any sign at x equals to a, then f has neither local maxima or local minima at x equals to a. So with this change of sign, this f dash of x change of sign will be derived from f double dash of x. Currently we are just showing you this change of sign with f dash of x only, but later on we'll also understand f double dash of x. That will define the sign of f dash of x. So what does this mean? Around this x equal to 0, my this derivative is positive and positive again, okay, positive again, and after this also it is positive, okay. So before also positive, after also positive. So f dash of x does not change its sign, right? It does not change its sign. It is positive before and it is again positive, okay, but in between it was going to 0. So that won't be a local maximum minima. That won't be a point of local maximum minima, okay. This isn't a point of local maximum minima, because just before this the value was low, just after this the value is high. So this is like a monotonically increasing function. We have already studied this. This is a monotonically increasing function. This is not a point of maxima or minima, okay. So after solving these questions, we'll understand this better, okay. So what I wanted to do is, I will give you homework, okay. So you try to solve this question, take the screenshot and you solve this question, and the next lecture will solve all this question, then this question, okay. You will need the help of wavy curve method, okay. I'll show you how to use wavy curve method, that we'll understand. Then find where the function f of x is increasing and decreasing. And yeah, I think this is the last question. Again the same question, and find where f of x is increasing and decreasing, okay. So you take the screenshot, you solve this, and I will see you in the next lecture. Thank you for watching.